Okay, this is Giancoli AP Edition, 7th edition. We are in Chapter 10, Fluids. We'll be working problem number 7, which is a level 3 problem. Always a good time. Jump into it. This problem reads, the Earth is not a uniform sphere, but has regions of varying density. Consider a simple model of the Earth divided into 3 regions, inner core, outer core, and mantle. Each region is taken to have a unique constant density, the average density of that region in the real Earth. So you're given the 3 regions there, each with their own radius, as far as where they apply, and then the density of each region. Question A, or part A, reads, use this model to predict the average density of the entire Earth. And then in part B, we're going to use the radius of the Earth and its actual mass to determine the actual average density. That's actually an easier calculation than part A. But then we're going to compare that as a percent difference with part A. Again, that by itself not a difficult problem. Part A is definitely the more difficult part of this problem. So go ahead and take a moment to wrap your brain around that and see if you can come up with a plan. Now, the thing they're asking us for in this problem is a prediction of the average density of the Earth based on these values we have up there. Now, we have 3 different regions, each with their own radius. The average density of the Earth, at least the prediction, density, as we know, is defined as mass per unit volume. And for this problem, in part A, we're predicting this density. And to accurately calculate that, we're going to need the mass of all these regions divided by the volume of all these regions. So to do that, I'm going to need the mass of the inner region plus the mass of the outer core plus the mass of the mantle. Now we could also add up all the individual volumes down here, but since these are all put into one large giant sphere with this outer radius here, I can just keep this at the total volume still. The tricky part comes in calculating each of these masses. To calculate those, we're going to have to use this relationship between mass and density again, this generic equation of density equaling mass divided by volume. I'm going to rearrange this so I can calculate each individual mass based on their individual densities and volumes. It can get confusing when you're using the same equation in multiple locations. This often happens in problems like this. So to calculate the overall density, I need the mass of the inner core, which would be the density of the inner core, which is a number I have, times the volume of the inner core, plus the density of the outer core times the volume of the outer core, plus the density of the mantle times the volume of the mantle. We're going to divide all that by the total volume. Now here's where it gets a little tricky, or even more tricky, with these volumes. The inner volume is going to be easy to calculate because I have a inner sphere with that radius. To calculate each of these subsequent volumes, I'm going to need to take the outer radius to calculate the volume of that sphere, but then subtract off the inner radius sphere because the inner part of that sphere is not included in that region's density. Take a moment to make sure you understand that before we move on. Now, volume for a sphere, if you don't remember, we can look that up, or if you remember, it's 4/3 pi radius cubed. So as I continue making substitutions here, we have the density of the inner times the volume of the inner, which is 4/3 pi r cubed, and that's the radius. I'm going to call this the radius of the inner, this the radius of the outer, and this the radius of the mantle, recognizing that there's the inner radius I have to remove. That's the radius of the mantle, cubed, Now I have the density of the outer. For the volume of the outer, notice for these next two volumes, I could make those volumes be 4/3 pi r. Don't use O because I've already used O for the outer. Let's say radius 2 cubed minus 4/3 pi radius 1 cubed. That would be the outer radius and the inner radius for any given sphere that has another sphere inside of it. That'll let me calculate each of these next two volumes. And to do that, it'll be a little cleaner to factor out the 4/3 and the pi. And just get the outer radius cubed minus the inner radius cubed. That'll make these a little simpler. So for the outer core, we make this 4/3 pi. The outer radius for this one is this thing I'm calling the radius of the outer core, cube, minus this radius of the inner core that is not included in this outer core. I need to go back and fix an oops here. That's the radius of the inner core back there. If you caught that, good on you. And I'm going to make some room here. So I also now calculate the mass of the mantle by multiplying its density times 4/3 pi. In this case, the radius of the outer portion of the mantle, this thing I'm calling Rm, minus the portion that is not included in the mantle, which is going to be the radius of the outer core. Now, this gives me all of the masses of each of the individual regions. Or divide that by the volume. Now for the entire sphere, again, it's 4/3 pi r cubed. In this case, it's the radius of the mantle that we're dividing by. And this should give us our model for our overall density of the planet. Now, there may be some ways to get creative with how we distribute these different radiuses around to try to get something to cancel. Not sure how much of our time is going to be well spent investing in that. However, you can see that each of the masses in the numerator has this 4/3 pi term that I can factor out, which is also in the denominator. So I can cancel all those 4/3 pi's, and that's going to save me some time with my calculator. And so this simplifies down to the density of the inner, radius of the inner cubed, plus the density of the outer, radius of the outer cubed minus radius of the inner cubed, plus the density of the mantle, radius of the mantle cubed minus radius of the outer core cubed, divided by the radius of the mantle cubed. And again, like I said, you could distribute these densities through and group them up by radius instead. I'm not sure that's really worth our investment. We're just going to go with what we have here. Because I know each of the densities of each of the regions. I know the outer radius of each of the regions. I know the radius of the overall sphere. And so I now have the thing I'm looking for in terms of numbers that I have. We're ready to plug in and get our answer. Okay, having copied the table down lower so we can get the numbers directly there. The density of the inner core is 13,000 kilograms per cubic meter, multiplied by our inner radius cubed, which is the 1,220 kilometers cubed. Now notice we have a unit mismatch here. We may have to deal with that. We'll see. Next one, we have the radius of the correction, the density of the outer core, which is 11,100 kilograms per cubic meter. We're going to multiply that by the difference of the cubes of the radiuses. So the outer radius, the outer core radius is 3,480 kilometers. Cubed minus the inner, which is 1,220. And now for the last mass, we're going to use the density of the mantle, which is 4,400 kilograms per cubic meter. And again, we're going to take the difference of the cubes of the radiuses. So it's 6,380 and 3,480. 6,380 kilometers cubed minus 3,480 kilometers cubed. That's a lot of numbers. We're going to divide that entire sum of masses effectively by the radius of the outer mantle, which is the 6,380. Cubed. Now, as I said, we have a unit mismatch here between the kilometers cubed here and the meters cubed here. But notice I've got a kilometer cubed term in each term in the numerator. I'm also going to get kilometers cubed in the denominator. So all those kilometers cubed will end up canceling. I'm going to end up with just a kilogram per cubic meter unit, which is a density, and that's the thing I'm looking for. So units aren't going to be as big a problem as I thought. So go and pick up your trusty calculator, go through these numbers, and see what you get. Okay, once you complete that calculation, you should get a number in the vicinity of 5,500.588. Again, this is approximate. And again, because of all of our cubic kilometers canceling, we're left with kilograms per cubic meter. Debatable how many significant figures we had in our original problem up here because of the zeros that are ambiguous. Let's be generous and say that that is 4 significant figures here. Would round our final answer to 5,501 kilograms per cubic meter. Now that's our estimate based on our model. And that answers part A, and that is the hardest part of this problem. Now we're ready to move on to parts B and actually B contains both the next parts. We're going to calculate the actual density based on, again, modeling the Earth as a sphere with the outer radius of 6,380 and that mass, and then compare these numbers. So a much simpler calculation for part B, again using our definition of density. In this case, we have an actual mass, 5.98 times 10 to the 24th kilograms. Divide that by, again, this is a model for our volume. The Earth is not actually a sphere. It's a little bit squashed in the middle, but it's close enough for modeling. Again, we're going to use the equation for volume of 4/3 pi r cubed. And so we're going to use 4/3 pi, radius of 6,380. Now we could unit convert this later. This is going to give us kilograms per cubic kilometer if we go the way we're going. If we want to avoid the unit conversion later, I can convert these kilometers to meters now. Remember, K stands for 1,000, so that's 6,380,000 meters. So we're just going to add 3 more zeros here. cube our radius to make that a volume. And now we're ready to calculate again. Go ahead and do that and see what number you get. And once you complete that calculation, you should get a number that looks somewhere in the vicinity of 5497.314-ish. And again, that's kilograms per cubic meter. On the previous calculation for reasonableness, is 5501 a reasonable number? Well, it's between these two, so it's less than the least dense part, but more dense than the most dense part. And as you get further out, the volume increases dramatically, so it should be weighted toward this one. So this number seems reasonable. And the fact that this number comes out relatively close to the estimate should give us a little bit of comfort. Again, that's an approximate number. So our density for part B, when you round to the same number of significant figures, is 5497 kilograms per cubic meter. And for the final part of this question, they want to know the percent difference. Determine the actual density and compare it as a percent difference with the one you determined in part A. So you're doing percent difference. It was covered much earlier in the book. This is our, they're calling it actual, but again, it's modeled a bit on the sphere because it's not exact. But to get our percent difference, we're going to take our actual, we're going to subtract off our estimate from before. That'll give us the actual difference between the two. Now to get percent difference as compared to the estimate, we're going to divide that by the estimate. That'll tell us what percentage of that original number we're off by. We're going to take our 5497. These are all in kilograms per cubic meter, both of these numbers and this denominator number. So I'm not going to bother using them. They're all going to cancel. Divide that by our estimate from part A. And this is about, that's a pretty small number actually. It's only about 4 off. It's a very small number. So we should expect a very small percent difference. Go ahead and calculate your number and see what you get. Now, because of the way I arranged this, you get a negative number. That's okay. We're going to just take the absolute value. We're just concerned about how far away we are. We're not concerned with whether it's positive or negative. If you calculate that as expected, you get a very tiny 0. Move that decimal twice. You get 0.073-ish percent difference between the answers of part A and part B. So while neither one is exact, they're both pretty consistent. And again, that should make you feel reasonably comfortable with these answers. That finishes this lengthy level 3. On to the next.